Okay, so if I have a function whose derivative is f of x equals 5x minus 4, what would the original function be? Just x to the 5th, right? And some different notation on the worksheet that I just gave you, I called the derivative f prime of x. This time I said the derivative is f of x equals 5x to the 4th. So it just depends on how they decide to use notation for this. Sometimes if they use f of x as like our derivative, they will use a capital F to show that that is the integral of that function. This is one reason why I've told you a couple times it's really important on FRQ questions, if they use a lowercase r, use a lowercase r. Do not write it as uppercase r. If they use an uppercase T, use it as uppercase T, because they might think that you're trying to do something there that you're really not, if you just change it to the other case. Now, this is not our only answer we could have. Somebody give me another one. Alright, I don't know how close that is to whatever you said, but alright, that also has a derivative of 5x to the 4th. But what we are going to do most of the time, whenever we are doing, this is called infinite integration. We'll talk about definite integration, actually maybe Friday. So whenever we do this, what we typically do here to show that you can have any constant added to the end is we put a plus c. Typically they use a capital C, although it doesn't really matter there. And that is our constant of integration, showing that we can have any number added to the end there. And you just see a note about that notation here. Capital F of x is an antiderivative of f on an interval I if f prime of x equals f of x for all x in I. So that capital F is being used as the antiderivative. The word antiderivative and integral, those can be used interchangeably. So an antiderivative is doing the reverse of taking a derivative. That also a lot of times is called an integral instead of being called an antiderivative. Those are sort of interchangeable there. Okay, questions? Okay, so a little bit of notation that we need to look at here. We have certainly used like f prime of x equals, let's just use, well, let's see. Let's just call it ax to the b. Ax to the b power right there. We certainly will see that notation sometimes, and then we would say f of x would be x to the b plus 1, and then over here we'd have a over b plus 1. Right there. That is one way that we might see it. We also might see that same thing where maybe f is not called f prime, it's called lowercase f, and our function is called capital F. Another way that we used to denote a derivative was dy dx. Okay, so let's say that we've got dy dx equals ax to the b power. Okay, so this hopefully will kind of explain a little bit why we have whenever we have that integration, while we put that like dx over there. This is technically what we call a differential equation, and in Chapter 7, we will learn how to do a lot of different things with differential equations. But this is a very, very simple differential equation. In order to solve a differential equation, you have to have all the x stuff on one side and all the y stuff on the other. So what I would have to do here is I'd have to multiply this side by dx to get rid of this, and I'd have a dx over here, which means I've got dy equals ax to the b power times dx. And then what I would be doing is I would be integrating both sides of that. And this dy doesn't have anything with it. It's like there's an invisible 1 right there. So we are integrating that left side with respect to y, which means right now it's like I've got, actually right now it's like I've got 1y to the 0 power, right? So I would increase that power by 1 to get y to the first, and then I would divide out front by 1. This is just y, right? And that happens every time, so we usually don't walk through it with this notation right here. And then over here, we would use our rule, so we would have x to the b plus 1, and then a over b plus 1. So a over b plus 1, x to the b plus 1 here. And then when I've integrated both sides, I can have any number added to the end. So I should have done this right here also. So I would put that plus c on the end, showing that I could have any constant added to the end there. Now, we did the same thing here. This is just a little bit different notation whenever we have that dy dx. You know, most of the time if I see something like this and they give me dy dx and ask me to find y, I don't necessarily show all the work on that. I just integrate there. Okay. All right, so let's do some problems. Find the antiderivative capital F of x for each function f of x. What would I get for number 1? I would get capital F of x equals 8x. You are almost right. Plus c. You want to always put that there. If it is infinite integration, which is just general, we're not like looking at an area under the curve from 1 to 7. It's just general integration. Always make sure you put the plus c. It's really important to remember it. You will not be able to do differential equations at all if you don't do that. Oh, what about 2? Okay, good. If we think about what's happening there, we would have, this is x to the 0 power, right? So if we think about using our rule, we can use our rule even on this one. I'm going to write it out long ways. You don't have to do this. You would have x to the first power. You would have 0 divided by 1. And then you'd have a plus c. But 0 divided by 1 is 0. 0 times x is 0. So you just get f of x equals c for that. Okay? Who can do number 3 for me? I'm going to try. All right, Kayla?
Capital F of x equals
5x squared plus 3x plus c. Beautiful. And you can always check these really easily by just taking that derivative to see if you get what you should start with, right? Then this last one, let's see. Lydia, what would I get for that last one?
capital F of x equals x to the 4th minus 3x to the 2nd plus c.
Not quite. We do need a plus c. What happens to that 2 right there?
Oh, we're in +2x.
Plus 2x. Now, what Lydia's brain probably did right there is it started taking the derivative halfway through, right? Because what is the derivative of 2? 0 goes away, you don't have it. But when we're integrating, this has got like an x to the 0 with it. We increase that exponent by 1. That gives us x to the first. We divide by 1 and get 2. What I usually find is that students do not have any trouble at all taking a just regular derivative until I teach them how to integrate. And then they may start halfway through just taking a derivative or integrating instead of the other. So be careful with these shortcut rules and make sure you know which way you're going with this. All right, so. Oh, oops. Okay, 5 and 6. Smith, what about number 5?
I didn't mean for you to call me. Hang on.
You can do it.
I just call somebody different. It's going to take me a little bit here.
You can do it.
Where's going to be 8? Calc of x equals 8x. That's good.
Good.
Minus 9x to the third.
Perfect.
Plus 10x.
Good.
Plus c.
Plus C. All right. All right, Troy, what about 6? Six is weird. What should we do for 6 before we try to integrate it? Let's do negative exponents. Negative 2x to the negative third plus 3. So then, Troy, what will we get whenever we integrate that? Okay, increase by 1. You get 1 when you divide. Yep, that looks great. Okay, so the rule is always going to be the same for this, but you are going to need everything to be in just regular exponential form first before you can take the integral. There. All right. Some properties of integrals compared to their differentiation rule. So, like, for example, to take the derivative of c, we would get 0. So when we integrate 0, we get c. To take the derivative of k times x, we just get k. If we integrate just the k, we get k times x plus c. All right. If we want to take the derivative of f and x separately, we can do that. If we want to integrate f and g separately, we can do that. And then our rule for our derivative is that we multiply out front by the exponent and then subtract 1 from the exponent. Our rule for our integration is that we add 1 to the exponent, divide out front by that number, which we've already kind of looked at. Okay, so some of the questions that you're going to get on your homework are going to ask you to solve a differential equation. This is like I was just showing you on that notation earlier. Technically what you're doing is you're multiplying both sides by dx, which gives you dy equals 5x dx. And then you're integrating both sides. And over here on this left side, now let me do some. Oh, actually I didn't do this on this last time. On this side we would get y plus c, right? And over here I would get x squared, and then I got to do 5 divided by 2, so 5 halves x plus c. I'm going to call this c1, I'm going to call this c2. Now, c is an unknown value, right? So I don't really like having the two C's there. Would it be okay if I did this? Like subtracted this C over to the other side. So I got y equals 5 halves x squared. Now, if I have an unknown value and I subtract an unknown value, what is it going to give me? It's C2 minus C1. Do we know what that is? Does it give us any more information than just an unknown value, right? An unknown value minus another unknown value, still just an unknown value. So what you can do is you can just put those like together as one C. Because it is an unknown value, if we do something to it, we don't really have to change it because it's still unknown. So what we're going to see most of the time whenever we do this, like if we look at example 8, technically you would multiply both sides by dx, and then you got dy equals 8x to the third plus 9x squared minus 4 dx, and you're going to integrate both sides. And when you do this, there's no need to put that plus c over on the left side. You can just add the c over on the right side. It will cover both sides of the equation as long as you're integrating both sides at the same time. So for this, we're going to have x to the 4th power. We got to do 8 divided by 4, which will give us 2. We're going to have x to the 3rd power. 9 divided by 3 will give us 3. We get a minus 4x plus c. So what I did over here on example 7 with the C1 and C2 is correct, but unnecessary. You can just add the c over here and it covers both sides. Okay, these are really just asking you to do the same thing in a different way. We will eventually get to looking at differential equations where we do a lot more with it, but right now it's just going to be a different way of asking the same question. All right. Okay, so if we do number 9, Lily, what would we get for number 9? Correct. So your exponent right here is 1. I a lot of times have to do it like step by step. So I have to add 1 to that exponent, so it'll give me 2. And then I divide the number out front by that exponent. Right there, so 5 halves. Perfect. And what do we need with it? Plus c. There we go. All right, number 10. We can't really do number 10 like it is right now. What should I do? Let's make that x to the 1/2 power so that I can use my rule. Now, sometimes a lot of students get mixed up with these fractions. You need to add 1 to the exponent. You're going to get x to the 3 halves. And then you have to divide out front by that 3 halves. Okay, there's a 1 there. You're dividing it by 3 halves. Now, if you're really good with fractions, you can do this part in your head. But some of us may or may not be great with fractions. So we got to do 1, dividing fractions, easy as pie, flip the second, multiply 1 times 2/3, which is going to give us 2/3. Okay, there. All right, let's see. Bo, what about number 11? What are we going to have to do to number 11? I do not, no, we will not have 5 for that. What I would do for this one is I would change it to make it x to the -4 power first. So we will have an x to the -3 because we got add 1 to -4. That'll give us -3. What will we get out front? What number do we have out here? We had a 1. We've got to divide it by the new exponent, so that's a -1/3. Then we'll put a plus c. Now, we probably will do this where we do -1 over, and then we'll put 3x to the 3rd back down there on the bottom. For that. So if you got a fraction, you need to make it a negative exponent first. Oh boy, look at 12. We do not have a quotient rule yet. We do not have like a product rule or something that we could use for this. We don't have that yet. All we've got is our shortcut power rule for this. So x plus 5 over x to over the square root of x has to be changed into something that we can use the power rule for here. Okay. You're saying like move it to the top and make it x to the -1/2. X plus 5. Like that. Okay, I like that. Then what would you do? We don't know a product rule for this. Can't. We can distribute right here. So when you multiply x to the -1/2 times x to the first power, you're adding the exponents. So that's going to give you x to the +1/2. And then you'll get 5x to the -1/2. Another way to think about that, besides moving it up, is that you could do a love connection for this. So it'd be like x over x to the 1/2 plus 5 over x to the 1/2, and then you could simplify that. You'll get the same thing here. But either way, we need to do this first. So then, whenever I integrate this, I got to add 1 to the exponent. So that's going to give me x to the 3/2. And then that means I got to do 1 divided by 3/2 out front. And if you're really, really good at doing fractions in your head, you can do that in your head. But I usually find students mess it up when there's fractions. So write the extra step if you need to. And then we're going to have over here, if I raise my exponent by 1, I'll get +1/2. And then I've got to do 5 divided by that 1/2. And I'll put a plus c on the end. So 1 over 3/2, we just did that a minute ago. We get 2/3 x to the 3/2. And then 5 times 2 over 1. Why is it not working? It's going to give us 10. Oh, that's a plus right there. 10x to the 1/2 plus c. Okay. All right, question.